Okay, now that we've seen how to apply linear programming to solving applications in two variables, let's look at how we would do it with a larger number of variables, more than two, on up to as many as we need. The method we use for this is called the Simplex method, and it's only works for maximization problems, not for minimizing, at least the way we're going to show it here. And it involves converting all the inequalities into equations so that we have a system of equations, and then we apply matrix operations, row operations, to that system of equations. So let's do our standard maximization using slack variables. First of all, we have our general linear programming problem where we have the variables x1, x2, x3, up to xn, and we have an objective function that involves those variables that we want to maximize the value of. And then we have constraints that are also in terms of those variables, where you have B1, B2, and so on. Those are just numbers that are the coefficients of those variables. So to maximize it, we're going to take all of those constraints. We assume, because all of the variables have to be non-negative, so that means they have to be greater than or equal to 0, we can assume that constraint and not worry about writing it. It's not going to become part of our system of equations. All of these constraints have to be written in such a way that this is always less than or equal to, and C is always non-negative. So it's either 0 or positive. So here, for this system, this is a legitimate system. There's our variables x, y, and z. This is less than or equal to, less than or equal to. These, remember, we don't worry about because those are assumed. So less than or equal to, less than or equal to, and both of those are positive. So that's a legitimate setup for what we're going to do here. Again, this one, can we ignore the fact each variable has to be greater than 0? We assume that each of these is less than or equal to, and each of these is positive, or non-negative at least, with the 0. So those can be used. This one does not fit because this here is greater than or equal to. In order to adjust it to make it less than or equal to, that would become negative. To flip that inequality, we'd multiply the whole thing by a -1, and we would get negative 2x minus z is less than or equal to -7. Can't have a negative value there. So what we're going to do then, let's say we have this problem here where this is our objective function that we want to maximize, and these are the constraints. Again, we're going to ignore x greater than 0, y greater than 0, z greater than 0. Those have to be true. We're assuming those to be true. So then for an inequality, the definition of an inequality, if we say that a is less than b, that means that a plus some positive value c equals b. This value c is what's referred to as a slack variable. So that's what we're going to do, is we're going to put that value in to each of those inequalities to convert it from an inequality into an equation. So that first one that was 2x plus 2y plus z is less than or equal to 10 becomes 2x plus 2y plus z plus s equals 10. And then we do that for each of them. So x plus 2y plus 3z is less than or equal to 5. This becomes x plus 2y plus 3z plus t equals 15, instead of being less than or equal to 15. And then our objective function gets adjusted so that everything gets put on the side with p. So instead of p equals 3x plus 2y plus z, we subtract the 3x, we subtract the 2y, we subtract the z, put them all on the same side as p. Because to work with matrix operations on a system of equations, all of our variables have to be on the left side of the equation. Now I moved x, y, and z over here just to line them up. Again, for matrix operations, we have to line up our variables in columns. So this problem here, this general problem, will become, this first inequality What we do is we add that first slack variable to make it equal C. Second inequality, we add the second slack variable, just call it S2 to make it equal the next constant, and so on. Then our objective function becomes P, and then minus each of the terms that was in the objective function there, equals 0. So let's look at a simpler version, an actual version with numbers in it instead of the general application there. So here, this first constraint, 2x plus z plus s equals 7. We added that slack variable to get rid of the inequality. This will be negative x plus 3y minus 6z. We'll use t for that slack variable to make it equal 6. The next one, x plus y plus z is less than or equal to 15. Well, x plus y plus z plus u equals 15. Then for objective function, we still have p. We subtract each of these to move them over to the left side. So it's negative 2x. Negative 3y becomes positive 3y minus 3z plus p equals 0. That is now in a system of equations that we're going to use matrix operations. So the simplex method really is talking about how we perform those matrix operations. So we have this system of inequalities and the constraint with all these unknowns. We're going to put it into a matrix, and they actually use a table in this textbook, but it's really matrix operations that we're doing. We know that the maximized points are at the vertices, at the corners, but this could be more than 2 dimensions. It could be 3 dimensions, or it could be in an abstract 4 or 5 dimensional figure. So we have to move from vertex to vertex, corner to corner, and evaluate it until we find the one that's optimal. And the way we do that is called pivoting. We get to a corner, we find the value of that corner, and then we pivot to get to the next corner. So geometrically, what the simplex method is doing is we're starting at 0, 0, where all the variables equal 0, the origin. And then we're moving out, but we have a mathematical process to decide what direction we move in. Now the visual here connected to what we're actually going to do, it's really tough to make that visual connection. So we're not going to try to, we're just going to follow the process. So let's maximize this objective function, p equals 3x plus 2y plus z, under those constraints. So our equations, 2x plus 2y plus z plus s equals 10 now. X plus 2y plus 3z plus t equals 15. And the objective function, we move this over, so we've got negative 3x minus 2y minus z plus p equals 0. That is our system of equations. We're going to put them into a table, which they call a tableau, so that we can do those matrix operations with them. So notice on top, we just label the x, y, z, s, t, and p. Then this is that constants over there. We just leave that blank. Eventually, we're going to come back. We're going to label this S, T, and P over here. So along the top, we've got those names to keep track of what columns we have there from our system of equations. And if you remember, when we have matrices, we can do row operations. We can replace a row with a combination of other rows, or we have to combine that row with a combination of other rows. Here they're talking about if we simply rearranged it, we can come up with this system of equations. They're kind of getting into the theoretical side of it. I'm going to skip over that a little bit. So we can get a family of solutions. So there's probably going to be more than one point here that gives us the same maximum value. We're going to get to the first one. They're the most accessible one. So here we could get that particular solution. S equals 10, T equals 15, and then the other variables all equal 0. That is the basic, we call the basic solution, where all the relevant variables are set at 0. And then we have so that's really, it's the basic solution where we start everything, but it really doesn't mean much. It's never going to be the maximum value. Doing nothing never maximizes profit or whatever we're looking to maximize. So we're looking for one of the active solutions and non-basic solutions. So they look at these here. They call the S, T, and P active variables. They're the variables that are driving the action that we do here. The X, Y, and Z are the passive or inactive variables. They're telling us what to do, but they're really not doing anything with the solution. So to obtain these directly from the tableau, we got all the active variables correspond to the cleared columns. Columns with only a cleared column means it has only non-zero entries. And then we can calculate a value here. So right now, if we put in X, Y, and Z equals 0, well, that means all this is basically gone. Well, S is equal to 10 divided by 1, T is equal to 15 divided by 1, and P would be equal to 0 divided by 1. We would have those values just by reading them out of the tableau of the table. So as an additional aid to recognizing which variables are active and which ones are non-active or inactive, we label each row with the name of the corresponding active variable. So like I said, this one gets labeled as an S because we're using the S as the slack variable. This gets labeled with T because we're using T as a slack variable. This one gets labeled with P because that's our objective function. Now we need to move to a different vertex or corner point of this abstract, or in this case, I guess, three-dimensional object. And to do that, we need to figure out which direction we're going to go. And the process or the direction is called a pivot. And the first part of that pivot process is selecting the column. And that column is, if you look at the bottom row, will be the first column that has a negative value in that bottom row. And then within that column, we'll choose a pivot item and we'll work from there. So choose the pivot. First, we choose the column. That is the column, like I said, if you look at the bottom row, it's the first column that has a negative value. So looking in this tableau, there's a negative value right there. And most of the time, it will be that first column the first time you do a pivot. So that's going to be our pivot column. Now within that column, we have to choose the pivot. That pivot is going to be the number that has the smallest value if we take that end amount, that constant amount at the end, and divide it by the value in the column. The smallest one is the one that we're going to use. So in this table here, 10 divided by 2 gives us 5. Your 15 divided by 1 gives us 1. So we're going to use the smallest one, the 2. That is our pivot. So it's in the pivot column, because that was the first column with a negative value down here. And that's the one that had the smallest test ratio. Now the pivot has to be positive, so that rules out using the -3. We can't use that. Couldn't use a 0 as well. Now, what choosing that pivot means is we're going to use that now to eliminate these other values in that column. Those values we want them to make them go away. And to do that, we're going to use our standard matrix operations. Multiplying one row by a value, multiplying another row by a value, and then combining them to replace one of the rows. Now again, all entries in the last column should remain non-negative. So the column on the very end here should all state positive values or zeros. Now, because the X column is no longer active, we cleared it out. We got rid of one of our row values. This is what we call the departing variable, because it is the row that we're using as our pivot. And this is the column that we're pivoting, so that X is actually going to replace the S over on the left side. That's going to help us when we get all done with this, figure out what does that row tell us? What value in the problem is that row giving us? So now, like we said, we have to use this top row That's our pivot, which means we use this row to get rid of those values in that same column in the other rows. So to get rid of the 1 here, what we would have to do is we would have to take 2 times the 1 minus the 2 in the top row. So what this is saying, 2r2 minus 1 is saying we're taking every value in the second row, we're going to multiply it by 2, and then subtract the corresponding value in the top row. So what does that mean? Well, 1 times 2 is 2, minus 2 is 0. That's what we wanted, was a 0 there. 2 times 2 is 4, minus 2 is 2. 3 times 2 is 6, minus 1 is 5. 0 times 2 is 0, minus 1 is negative 1. 1 times 2 is 2, minus 0 is 2. 0 times 2 is 0, minus 0 is 0. 15 times 2 is 30, minus 10, this is going to be 20. On the bottom row, it's saying we're going to take 2 times this third row and add 3 times the first row. So negative 3 times 2 is negative 6, plus 2 times 2 is positive 6, that makes that 0, which is what we want. And we'll continue that all the way down that line to replace those bottom 2 rows now with the matrix operations that we did. Notice these have become 0. Now in this example, there are no more negative values in this bottom row, which means we are done. So what this is telling us, if there were any more negative values, we'd go back to step 3 and repeat it. But they're not, so now we can just read off the answer. I'm just going to take it out of the table here. This row is active in X, so to find the value of X, we take this value 10 and we divide by the value in the X column, 2, so that's going to tell us X equals 5. This is in T, so there's 20 here, there's 2 in the T, 20 divided by 2 is 10, T equals 10. P, there's 30 here, so we're going to divide by the P of 2, that's 15, P equals 15. All of the other variables equal 0. So Y equals 0, Z equals 0, S equals 0. So remember though, that the solution for X, the first active variable is not just X equals 10, but it's X equals 10 divided by 2. That's why I divide by the 2 here because there's a 2 in that X column. So we got X equals 5, T equals 10, and P equals 15. All the other variables, like we said, are 0. They're inactive. So that is the maximization for this function, for this situation. So there is some explanation on that step 4 as to how did we know that it had, why did we have to use the one with the lowest test ratio? And what it basically comes down to, I'm not going to go through their little proof here, but what it comes down to is if we use something with a larger test row or test ratio, we end up getting negative values where we can't have negative values. Remember that last column of the table has to stay positive. And if we chose a variable that did not have the largest test ratio, we would end up with some negative values there. We want to avoid that. So that's why we use the smaller test ratio to choose our pivot. Let's look at an application here. Now this one, and to find an application simple enough to do, we do reduce the number of variables. This one actually could be done with graphing and doing that feasible region, but let's do it with our slack variables and this simplex method. So back to the Acme Foods company, is making baby food. They make vanilla and chocolate pudding. For vanilla, it requires 2 teaspoons of sugar and 25 fluid ounces of water. Chocolate requires 3 teaspoons of sugar and 15 fluid ounces of water. Each day they have 3,600 teaspoons of sugar available and 22,500 fluid ounces of water. They will make no more than 600 servings of vanilla because that's all they can sell in a day. Their profit is 10 cents on vanilla and 7 cents on chocolate. So how many servings should it make of each in order to maximize their profit? So we're going to let X equal the number of servings of vanilla pudding and Y the chocolate. We know we've got the sugar, 2 teaspoons of sugar plus for vanilla, 3 teaspoons of sugar for chocolate. Our total of 3,600 per day. Water is the same thing. Our fluid ounces, 25 for vanilla, 15 for chocolate, 22,500 total for the day. Gives us these inequalities. The amount of sugar used, 2x plus 3y has to be less than 3,600. For the water, 25x plus 15y has to be less than 22,500. And they're saying note that that's divisible by 5. We'll reduce that one. Right here, we divided by 5 to reduce that to 5x plus 3y is less than 4,500. And you'll note we added in the inequality because we don't want to produce any more than 600 servings of vanilla pudding. So x is less than or equal to 600. So now we have 3 equations here, plus our objective equation. So we're going to have 3 slack variables. So we start out x plus s is 600. That's taking that x is less than or equal to 600 and converting it to an equation with the slack variable. 2x plus 3y plus t equals 3,600. 5x plus 3y plus u is our third slack variable equals 4,500. And then we have our objective function rearranged, put all the values on the left side. So that is going to now go into our tableau, basically our organized our matrix, different version of a matrix. So this was, now remember this was 1x plus 1s equals 600. There's a 1 in the x, a 1 in the s, and then a 600. Everything else is 0. We're labeling that s because s is the active variable. That's the variable we put into that to make that equation. Next, we had 2x, 3y, no s, 1t, and then 3,600. So same here. 2 in the x, 3 in the y, 0 in the s because there isn't an s, 1 in the t, there's no u, no p, and then equals 3,600. So we fill in the table in that way. Now we need to choose the pivot column. Well, looking on bottom, that's the first negative value in that bottom row. So once again, we're going to start with that row 1 as being our pivot, or column 1, I should say, being our pivot column. The pivot within that column, remember we take this number divided by the number in the column. 600 divided by 1 is 600. 3,600 divided by 2 is 1,800. 4,500 divided by 5 is 900. Well, the smallest one there is 600, so that's why we choose the 1 as our pivot. So that means we're going to use row 1 to try to get rid of these other values in that first column. So for the second row, I would have to subtract the 1 twice to make that a 0. So notice I take, oops, what did we do here? Oh yeah, we did row 2 minus row 1 twice, minus 2 times row 1. That's going to give me 0 here, and then I have to do the same with all the other entries. 3 minus 2 times 0 is still 3. 0 minus 2 times 1 is negative 2. 1 minus 2 times 0 is still 1. 0 minus 2 times 0, 0 minus 2 times 0 is still 0. 3,600 minus 2 times 600 is going to give us 2,400. This next column, we have to get rid of the 5. So we're going to do 5 times 1. So that's row 3 minus 5 times row 1. 5 minus 5 times 1 is 0. 3 minus 5 times 0 is 3. 0 minus 5 times 1 is negative 5, and we go on down the row. And then finally, this last one here, this is a negative 10. So to get rid of it, I'm actually going to add 10 times the 1. So it's row 4 plus 10 times row 1. Negative 10 plus 10 times 1 is 0. Negative 7 plus 10 times 0 is negative 7. 0 plus 10 times 1 is 10, and on down the line again. Well, there are still zeros in that bottom row. In the first example we did, after we did the first pivot, everything in the bottom row is positive, so we were done. But there's still zeros down there. So we picked the first one, which is going to be the negative 7. Up above, there's a 0 here. We can't use that, so it's going to be one of these 3's. So 2,400 divided by 3 is 800. 1,500 divided by 3 is 500. That's the smaller ratio, so we're going to use that as our pivot. So we have to use that to eliminate the values in that column of all the other rows. Well, this one's already 0, so we're not going to change row 1. To get rid of this, we just do 3 minus 3. So row 2 minus row 3, cancel that out. So 3 minus 3 will be 0. Negative 2 minus negative 5 will be a positive 3. 1 minus 0 will be 0, or 1, sorry, 0 minus 1 will be negative 1, and on down the line. And you can see we got those values, 0, 3, 1, negative 1, on down the line. But down here is a little trickier. We have a negative 7, and we're going to use that 3 to get rid of it. So we're going to do positive 3 times negative 7 is negative 21. Plus 7 times 3 is a positive 21. That adds up to 0. So 3 times row 1 plus 7 times row 3. And again, we fill that in right here. Now you'll notice there is still a negative value in that bottom row. So that means we're going to use that as our pivot column. Can't use the 5 because that's a negative number. 600 divided by 1 is 600. 900 divided by 3 is 300, so that's the smaller ratio, so that's why we use the 3. We're going to use that to eliminate the other values in that column. Well, there's a 1 here, so we're going to use row 1's got to get used. We're going to do 3 times row 1 minus row 2. So 3 times 1 minus 0 is just 3. 3 times 0 minus 0 is just 0. 3 times 1 minus 3 is 0. 3 times 0 is 3 minus 1 is negative 1. Right on down the line. 3 times 0 minus negative 1 is a positive 1, and right down the line. And then for this one, to get rid of that, we're going to do 3 times the negative 5 plus 5 times 3. So that's 3 times row 3 plus 5 times row 2. And then we do the same down here, 3 times row 4 plus 5 times row 2. And after we do those, again, these are basically matrix row operations. We get this table here, where finally all of the values in that bottom row are positive. Now notice, I should go back and explain what we did here on the side here. This was X was our pivot column, so X is our active variable. 1 was in the S row, so we replaced the S there with X. Notice that became an X because we used the X column to use that in that row. Now here, this next step, Y was our pivot column, so Y is going to end up going over here. We chose this as our pivot value in there, so that was our row, so that U is going to get replaced by a Y in the next table, right there. And then we used this S was our pivot column, so S is going to end up coming back over here. We used the value in the T row, so T gets replaced by S in the third one. So it is important to keep track of those variables over there, because that tells you what each of these values stands for. So now to get our values, this is telling us this column gives us the value of X, so we're going to use the X value and this value. 900 divided by 3 is 300, so X equals 300. This row gives us S, so we take the value of S as 300. 900 divided by 3, S is also 300. This row gives us the value of Y, so that's 9 and 9,000. 9,000 divided by 9 is 1,000, so Y equals 1,000. And the value of P, well, P is 9 here, 90,000. 90,000 divided by 9, the maximized value of P is going to be 10,000. So there we have completed that tableau to solve that equation. You see there's the values written out again. So to summarize, to use the simplex method, you take your constraints, again, you ignore the X greater than 0, Y greater than 0, and greater than or equal to 0, and all those. You turn all your constraints into equations by adding those slack variables. You turn your objective function into an equation with all the variables on one side. Then you put them in that tableau, into that tool. Again, you could use just a regular matrix if you prefer. You choose the pivots. The pivot's really just a way of deciding what matrix row operations to do. So that pivot just kind of makes sure that everybody's going through the same steps. That as we progress through the points, everybody's going to the same next point on that figure. We use those test ratios to decide which item to use in that pivot column to use as our pivot. And then once we've chosen the pivot, we got to remember that variable now goes to replace that column variable, replaces the row variable, the departing variable and our entering variable, and we get our solution. You get to that point, if there's still any negative values, of course, on that bottom row, you go back to step 3 and repeat until the bottom row is positive. And then, of course, you have the solution. And that is it. Now, that simplex method is tough. We'll do an example in our online office hours this week. It is tricky, and it's a little bit different way of thinking, and it combines a little bit of statistics with a lot of algebra and then our matrix operations.